It was 1930. A young physicist named Paul Dirac was working on a problem. He was trying to make two great theories of his time play nice with each other. One was quantum mechanics, the strange rules of the very small. The other was special relativity, Einstein's rules for the very fast. He wanted to write an equation that described an electron moving near the speed of light, following both sets of rules. He succeeded. He wrote a beautiful, compact equation, but it had a ghost in it. The equation worked perfectly. It described the electron's properties, like its spin, with stunning accuracy. But like a simple math problem that asks for the square root of 4, it gave two answers. The answer could be 2, or it could be -2. Dirac's equation had a solution for a normal electron with positive energy. It also had a solution for an electron with negative energy. This was a puzzle. Negative energy didn't make sense. An electron should not be able to have less than 0 energy. It would mean that electrons could just keep falling to lower and lower energy states, releasing infinite energy and making all matter unstable. Dirac thought about it. He came up with a wild idea. What if empty space was not empty at all? What if it was completely full of an infinite sea of these negative energy electrons? We wouldn't notice them because they were everywhere, a perfect uniform background. But he reasoned if you hit this sea with enough energy, you could knock one of these negative energy electrons out of its place. It would pop into our world as a regular positive energy electron, and it would leave behind a hole in the sea. This hole, this absence of a negative energy electron, would behave just like a particle. Would have the same mass as an electron, but because it was a hole in a sea of negative charges, it would have a positive charge. At first he thought this hole must be the proton, the only positively charged particle known at the time. But his own math told him the hole had to have the exact same mass as the electron. A proton is almost 2,000 times heavier, so his theory predicted a new particle, an anti-electron, a piece of antimatter. Most scientists thought it was a mathematical trick, a weird feature of an equation that didn't mean anything in the real world. An entire sea of invisible particles filling all of space seemed like science fiction. Then, in 1932, a physicist named Carl Anderson was studying cosmic rays. These are high-energy particles that rain down on Earth from space. In his cloud chamber, a device that lets you see the tracks of particles, he saw something strange. He saw a track left by a particle that curved in a magnetic field just like an electron, but in the opposite direction. It had the same mass as an electron, but a positive charge. He had found Dirac's hole. He had discovered the positron. Dirac's strange ghostly equation was right. Empty space was not empty. It was a seething, hidden reality. This discovery tore up the old picture of a quiet, passive vacuum. It revealed that the void is a dynamic stage where particles of matter and antimatter can flicker into existence from nothing and vanish just as quickly. This was the first hint that the simplest thing we can think of, nothingness, is actually the most complex and active place in the entire universe. Number 21. The universe is stretched by something in nothing. A single cubic meter of empty space contains more energy than all the matter in the entire known universe. This energy is pushing the universe apart, causing it to accelerate its expansion. We call this dark energy, but we have no real idea what it is. The value of this energy is so small and so specific, it's considered the single worst theoretical prediction in the history of physics. We used to think the universe's expansion was slowing down. Gravity from all the stars and galaxies should be pulling everything back together. It seemed obvious. Then came 1998. Two separate teams of astronomers were using powerful telescopes to look at distant supernovae. These are exploding stars that act like standard candles. They have a known brightness, so by seeing how dim they appear, you can calculate how far away they are. You can also measure how fast they are moving away from us by looking at their redshift, how much their light has been stretched. The plan was to measure the rate at which the expansion was slowing down, but both teams found the exact opposite. The distant supernovae were dimmer than they should have been. They were farther away than the standard model of cosmology predicted. This meant that sometime in the last few billion years, the expansion of the universe hadn't been slowing down. It had been speeding up, something was pushing everything apart, something was acting like anti-gravity on a cosmic scale. This was a shock. It was like throwing a ball into the air and watching it suddenly shoot upwards faster and faster. The discovery won the Nobel Prize in Physics in 2011. The cause of this acceleration was named dark energy. It's called dark because it doesn't interact with light. It's completely invisible. We can only see its effect on the universe as a whole. When we add up all the stuff in the universe, we find a strange cosmic budget. Normal matter, the atoms that make up you, me, the planets, and the stars, accounts for only about 5% of the total energy and mass of the universe. Dark matter, another mysterious substance that we'll get to, makes up about 27%. The rest, a whopping 68%, is this dark energy. The universe is dominated by something we can't see and don't understand. The best idea we have is that dark energy is a property of space itself. It's a kind of intrinsic energy of the vacuum. As space expands, more space is created, and this new space has its own intrinsic energy. So more expansion leads to more dark energy, which leads to more expansion. It's a feedback loop. This idea has a name. It's called the cosmological constant. It was first proposed by Albert Einstein in his theory of general relativity, but for a different reason. He put it in his equations to make the universe static, to counteract gravity and stop it from collapsing. When Edwin Hubble discovered the universe was expanding, Einstein called the cosmological constant his biggest blunder. It now seems he might have been right for the wrong reason, but there's a huge problem. Our best theory of particle physics, the Standard Model, can be used to calculate how much energy the vacuum of space should have. This calculation involves the energy from all the virtual particles that flicker in and out of existence. When physicists do this calculation, the number they get is gigantic. It's 10 to the power of 120 times larger than the amount of dark energy we actually observe. That's a 1 with 120 zeros after it. This discrepancy is known as the cosmological constant problem, or the vacuum catastrophe. It is one of the biggest mysteries in science. Why is the energy of empty space so ridiculously small compared to what our theories predict? We don't know. Something is canceling out almost all of that energy, but leaving just a tiny bit behind to drive the cosmic acceleration. Finding out why is a central goal of modern physics. Number 20, there's an invisible skeleton holding galaxies together. For every gram of normal matter, like stars and gas, there are about 5 grams of an invisible substance called dark matter. This material does not emit, reflect, or absorb any kind of light. It passes through you and the Earth as if you were not there. We know it exists only because we can see its gravity pulling on the things we can see. The story starts in the 1930s. A Swiss astronomer named Fritz Zwicky was studying the Coma Cluster, a giant collection of galaxies. He measured how fast the individual galaxies were moving. He found they were moving incredibly fast. So fast, in fact, that the gravity from all the visible stars in the cluster shouldn't have been enough to hold them together. The cluster should have flown apart millions of years ago. Zwicky calculated that there must be hundreds of times more mass in the cluster than he could see. He called this missing mass Dunkel Materie, or dark matter. For decades, his idea was largely ignored. Then, in the 1970s, an astronomer named Vera Rubin was studying the rotation of individual galaxies like our own neighbor Andromeda. She was measuring the speed of stars at different distances from the galactic center. According to Newton's laws of gravity, stars farther out from the center should move more slowly, just like outer planets in our solar system orbit the sun more slowly than the inner ones. But that's not what she found. The stars on the outer edges of the galaxies were moving just as fast as the stars closer in. The only way this could be possible is if the galaxies were embedded in a giant, invisible halo of mass, a sphere of matter that extended far beyond the visible stars. The gravity from this halo was what was keeping the fast-moving outer stars in their orbits. Vera Rubin's work provided powerful, undeniable evidence for dark matter. Since then, the evidence has piled up from many different sources, and we see its effects in gravitational lensing. This is when the gravity of a massive object, like a galaxy cluster, bends the light from a more distant object behind it. By measuring how much the light is bent, we can calculate the mass of the cluster. These calculations consistently show that there is far more mass than can be accounted for by the visible matter. The cosmic microwave background, the leftover radiation from the Big Bang, also has patterns in it that can only be explained if dark matter exists. So what is it? We know what it isn't. It's not just dark clouds of normal matter because we would be able to detect them in other ways. It's not black holes or neutron stars because there simply aren't enough of them. It has to be something new, some kind of particle that isn't part of the standard model of particle physics. The leading candidates are called WIMPs, or weakly interacting massive particles. These are hypothetical particles that don't interact with light and only interact with normal matter through the weak nuclear force and gravity. They are weakly interacting, which is why they are so hard to detect. They are massive, which is why they have enough gravity to hold galaxies together. Scientists around the world are running experiments to try and detect these particles. These experiments are often located deep underground in mines or tunnels to shield them from cosmic rays and other background radiation. They use ultra-sensitive detectors made of materials like liquid xenon or germanium crystals. The hope is that a WIMP will occasionally bump into the nucleus of an atom in the detector, creating a tiny flash of light or a small vibration that can be measured. So far, despite decades of searching, no WIMP has been definitively detected. The search for dark matter is one of the most important quests in physics. Figuring out what this invisible substance is will not only solve the mystery of the missing mass, but will also open up a whole new window into the fundamental nature of reality. It's a reminder that the vast majority of the stuff in the universe is hidden from us, filling the space between the stars. Number 19, space itself can ripple and ring like a bell. A collision between two black holes, each 30 times the mass of the Sun, that happened 1.3 billion years ago, released more energy in its final fraction of a second than all the stars in the observable universe combined. This energy was released not as light, but as waves in the fabric of spacetime itself. On September 14, 2015, those waves finally reached Earth and were detected. Albert Einstein predicted the existence of gravitational waves in 1916 as a consequence of his theory of general relativity. The theory describes gravity not as a force, but as a curvature of spacetime caused by mass and energy. A massive object warps the spacetime around it. When massive objects accelerate like two black holes orbiting each other, they create ripples in this fabric. These ripples, called gravitational waves, travel outwards at the speed of light. For 100 years, these waves were purely theoretical. They are incredibly weak. By the time a gravitational wave from a distant cosmic event reaches Earth, it stretches and squeezes the space it passes through by a minuscule amount. The change in length is smaller than 1,000th the diameter of a proton. Detecting such a tiny change seemed impossible. That's where LIGO comes in, the Laser Interferometer Gravitational Wave Observatory. It consists of two identical detectors, one in Louisiana and one in Washington State. Each detector is a giant L-shaped instrument with two arms, each 4 kilometers long. A powerful laser beam is split and sent down both arms. The beams reflect off mirrors at the ends and come back to the starting point. If the lengths of the two arms are exactly the same, the returning light waves should cancel each other out, and a detector will see nothing. But if a gravitational wave passes through, it will stretch one arm and squeeze the other by a tiny amount. This changes the distance the laser beams travel. They will no longer perfectly cancel out, and the detector will register a signal. On that day in 2015, both detectors registered a signal just milliseconds apart. The signal was a chirp, starting at a low frequency and getting higher and higher in pitch and loudness before abruptly stopping. This was the exact signature predicted for the final moments of two black holes spiraling into each other and merging. The data allowed scientists to calculate the masses of the black holes, how far away they were, and even the mass of the new, larger black hole they formed. The discovery was a monumental achievement, a new way to observe the universe. It was like we had been deaf our whole lives, and suddenly we could hear. Since that first detection, LIGO and its European counterpart Virgo have detected dozens of gravitational wave events. Most are from merging black holes, some are from merging neutron stars, the ultra-dense remnants of dead stars. One such event in 2017 was also seen by conventional telescopes. The collision created a flash of light, a kilonova, which allowed us to confirm that these mergers are where most of the heavy elements in the universe, like gold and platinum, are created. Gravitational waves are not traveling through space, they are oscillations of space. They are a direct manifestation of the dynamic physical nature of the vacuum. They show that empty space is not a static backdrop. It is a medium that can be disturbed, that can carry energy, and that can tell us about the most violent and energetic events in the cosmos. Listening to these ripples in space-time is opening up a completely new chapter in our exploration of the universe. Number 18, the afterglow of creation is everywhere. About 1% of the static you see on an old analog television, when it's tuned to an empty channel, is radiation left over from the Big Bang. This faint glow fills all of space. It's the oldest light in the universe. It has been traveling for 13.8 billion years. This radiation is called the cosmic microwave background, or CMB. Its discovery was an accident. In 1964, two American radio astronomers, Arno Penzias and Robert Wilson, were working at Bell Labs in New Jersey. They were using a large horn-shaped antenna to study radio signals from the Milky Way. But they kept picking up a persistent low-level hiss. It was coming from all directions, day and night, no matter where they pointed the antenna. They thought it must be some kind of interference. They checked everything. They even cleaned out the pigeon droppings from inside the antenna, thinking the bird's waste might be causing the noise. But the hiss remained. At the same time, a team of physicists at nearby Princeton University, led by Robert Dicke, was preparing to build an experiment to search for this very same radiation. They had been working on theoretical models of the Big Bang. These models predicted that the early universe must have been incredibly hot and dense. It would have been filled with a blazing hot plasma of particles and light. As the universe expanded, it cooled. About 380,000 years after the Big Bang, it cooled enough for protons and electrons to combine and form neutral hydrogen atoms. When this happened, the universe suddenly became transparent. The light that had been trapped in the plasma was now free to travel through space. This burst of light, the afterglow of the Big Bang, should still be detectable today. As the universe continued to expand, this light would have been stretched to longer and longer wavelengths, shifting it from visible light into the microwave part of the spectrum. When Penzias and Wilson heard about the Princeton team's work, they realized what they had found. Their annoying hiss was not interference. It was the echo of creation. They had stumbled upon one of the most important discoveries in the history of cosmology. They won the Nobel Prize for it in 1978. The CMB is a snapshot of the universe when it was just a baby, and it is remarkably uniform. The temperature of the CMB is the same in all directions, about 2.725 Kelvin, just a few degrees above absolute zero. But it's not perfectly uniform. There are tiny temperature fluctuations, differences of only about 1 part in 100,000. These tiny variations are incredibly important. They are the seeds from which all structure in the universe grew. The slightly hotter, denser regions had more gravity, and over billions of years, they pulled in more and more matter, eventually forming the galaxies and galaxy clusters we see today. The slightly cooler, less dense regions became the great voids in between. Satellites like COBE, WMAP, and Planck have mapped these tiny fluctuations in the CMB with incredible precision. By studying the patterns in this map, we can learn a huge amount about the universe. We can determine its age, its composition, the amounts of normal matter, and dark energy, and its geometry. The CMB is a treasure trove of information. It's a fossil from the beginning of time, and it fills every cubic centimeter of the supposedly empty space around us. Number 17, space is governed by a universal speed limit. The speed of light in a vacuum is 299,792,458 meters per second. This is not just the speed of light. It's the ultimate speed limit for everything in the universe. Nothing with mass can reach this speed, and nothing, not even information, can travel faster than it. This speed is a fundamental property of the vacuum itself. This idea came from James Clerk Maxwell in the 1860s. He was working on unifying the theories of electricity and magnetism. He produced a set of 4 elegant equations that described how electric and magnetic fields are related and how they change over time. When he solved these equations, he found something remarkable. They predicted the existence of waves of electromagnetic energy that would travel through space at a specific speed. He calculated this speed from the known constants of electricity and magnetism. The number he got was incredibly close to the measured speed of light. He realized that light must be an electromagnetic wave, but there was a strange thing about this speed. It didn't depend on the speed of the source or the observer. It was a constant. This was completely at odds with everyday experience. If you're on a train and you throw a ball forward, someone standing on the platform will see the ball moving at the speed of the train plus the speed you threw it. But Maxwell's equations said that if you were on a spaceship traveling at half the speed of light and you turned on a flashlight, both you and someone standing still would measure the speed of the light from that flashlight to be exactly the same. This puzzle was solved by Albert Einstein in 1905 with his theory of special relativity. He took Maxwell's result at face value. He started with the principle that the speed of light in a vacuum is the same for all observers. From this single idea, all the strange consequences of relativity follow. Time slows down for moving objects. Moving objects get shorter in their direction of motion. Mass and energy are equivalent, as expressed in the famous equation E equals mc squared. The speed of light, c, is not just a speed. It's a fundamental conversion factor between space and time. It tells us how much space is equivalent to a certain amount of time. It's woven into the very fabric of space-time. The reason nothing can travel faster than light is because it would violate causality. It would mean you could receive a signal before it was sent. It would allow for time travel into the past, leading to all sorts of paradoxes. The universe has a built-in rule that prevents this. This speed limit is a property of empty space. The constants that determine the speed, the permittivity and permeability of free space, are characteristics of the vacuum. They describe how electric and magnetic fields propagate through nothingness. If you were to change these properties, the speed of light would change. So the vacuum is not just a passive stage. It's an active participant. It has properties that dictate the most fundamental rules of the universe, including the ultimate speed limit. It's the medium that carries light, gravitational waves, and all other fundamental fields. And its properties are what make the universe work the way it does. Number 16, the universe might be a bubble in a larger multiverse. The fundamental constants of our universe, like the strength of gravity or the mass of the electron, seem to be finely tuned to allow for the existence of life. If these values were even slightly different, the universe would be a sterile place. This fine-tuning problem has led some physicists to consider a radical idea: our universe might just be one of many, a single bubble in a cosmic foam of other universes, each with different laws of physics. This is the concept of the multiverse, and It arises from several areas of modern physics. One of the most prominent comes from a theory called eternal inflation. The theory of cosmic inflation says that in the first fraction of a second after the Big Bang, the universe underwent a period of incredibly rapid exponential expansion. This theory does a great job of explaining many observed features of our universe, like why it's so big and so uniform. Eternal inflation takes this a step further. It suggests that this inflationary process might not have stopped everywhere at the same time. While our region of space stopped inflating and became the universe we know, other regions of space could still be inflating. These inflating regions would expand so rapidly that they would spawn new bubble universes, which would then cool down and form their own galaxies and stars. This process could go on forever, creating an infinite number of universes. Each of these bubble universes could have different properties. String theory, a candidate for a theory of everything, suggests that there might be a vast number of ways the fundamental laws of physics can work. The theory predicts the existence of extra spatial dimensions that are curled up and too small for us to see. The way these dimensions are curled up determines the values of the physical constants in our three-dimensional world. The number of possible ways for these dimensions to be configured is enormous, perhaps 10 to the power of 500. Each configuration would result in a different universe with a different set of physical laws. In this picture, our universe is just one of the lucky ones. Out of a near infinite number of universes, most would be inhospitable. They might collapse in on themselves instantly or expand so quickly that no stars could ever form. Some might not have chemistry, or they might have, forces that are too strong or too weak for atoms to be stable. We find ourselves in a universe with just the right conditions for life, simply because we couldn't exist in any of the other ones. This is called the anthropic principle. This is a controversial idea. The multiverse is, by its very nature, likely impossible to observe directly. We can't travel to another bubble universe. This leads some to argue that it's not science, but philosophy or metaphysics. However, proponents argue that the multiverse is a natural consequence of our best theories, like inflation and string theory. If those theories are right, then a multiverse might be unavoidable. The idea that our entire cosmos is just one small part of a much larger, unimaginably vast reality redefines what we mean by empty space. It suggests that the space beyond our observable universe might not just be more of the same, but could be an eternally inflating sea, constantly giving birth to new realities. Number 15, space can end without warning. The Higgs field, which permeates all of space and gives fundamental particles their mass, might not be in its most stable state. A random quantum fluctuation could, at any moment, trigger a catastrophic event called vacuum decay. This would create a bubble of a new, more stable kind of vacuum. The bubble would expand at nearly the speed of light, destroying everything in its path. We would have no warning. The Higgs field is a bit like a potential energy landscape with hills and valleys. The universe, as we know it, exists because the Higgs field is settled in one of these valleys. This is its vacuum state. The properties of our universe, like the masses of particles, depend on the specific value of the Higgs field in this valley. But what if this valley is not the lowest one? What if there's a deeper, more stable valley nearby? If that's the case, our universe is in what's called a false vacuum. It's stable for now, but it's not fundamentally stable. According to quantum mechanics, it's possible for the field to tunnel through the energy barrier, separating our false vacuum from the true vacuum. This is a purely random quantum event. If it happened, a small bubble of the true vacuum would appear somewhere in the universe. Inside this bubble, the laws of physics would be different. The Higgs field would have a different value. This would change the masses of fundamental particles like electrons and quarks. The strengths of the fundamental forces could also change. This bubble would be at a lower energy state than its surroundings. This energy difference would drive the bubble to expand. The bubble wall would race outwards at nearly the speed of light. As it passed over a region of space, it would instantly rewrite the rules of reality. Atoms would fall apart, stars would be extinguished, life as we know it would be impossible. Because the bubble expands so fast, we would have absolutely no warning. The end would arrive before the light from the event could reach us. So how likely is this? Is our universe living on borrowed time? Physicists have tried to calculate the stability of our vacuum. The answer depends very sensitively on the precise masses of two particles, the Higgs boson discovered in 2012 and the top quark. Using the current best measurements for these masses, the calculations suggest that our universe is in a metastable state. This means it is in a false vacuum, but the energy barrier to get to the true vacuum is very large. The probability of a tunneling event happening is incredibly small. The expected lifetime of our vacuum is fantastically long, billions upon billions of times longer than the current age of the universe. So it's not something to lose sleep over. But the fact that it's even a possibility is a profound statement about the nature of space. It tells us that the vacuum is not just empty, it's a physical object with properties that could, in principle, change. The very foundation of our existence, the stable background that we take for granted, might just be a temporary state. Number 14, space is filled with a ghostly haze of particles. Trillions of neutrinos, ghostly subatomic particles, are streaming through your body every second. Most of them come from the nuclear fusion reactions happening in the core of the sun. They travel at nearly the speed of light and interact so weakly with other matter that they can pass through the entire Earth without hitting a single atom. Neutrinos were first proposed in 1930 by the physicist Wolfgang Pauli. He was trying to solve a puzzle related to radioactive decay. In a process called beta decay, a neutron in an atom's nucleus turns into a proton and an electron. When scientists measured the energy of the electron that was emitted, they found that some energy was always missing. This seemed to violate the fundamental law of conservation of energy. Pauli suggested that a new, undetected particle was being created in the decay and was carrying away the missing energy. This particle would have no electric charge and a very tiny mass, which is why it was so hard to detect. He called it the neutrino, which is Italian for little neutral one. It took 26 years to finally detect a neutrino. In 1956, Frederick Rines and Clyde Cowan set up an experiment next to a nuclear reactor, which is a powerful source of neutrinos. They used a huge tank of water to detect the very rare interactions of neutrinos with protons. Their success confirmed that these elusive particles were real. We now know there are three types or flavors of neutrinos: the electron neutrino, the muon neutrino, and the tau neutrino. And they have a very strange property. They can change from one flavor to another as they travel through space. This phenomenon is called neutrino oscillation. The discovery of neutrino oscillations in the late 1990s and early 2000s was a major breakthrough. It proved that neutrinos must have mass, however small. This was a big deal because the standard model of particle physics originally predicted that neutrinos should be massless. This discovery is one of the few pieces of experimental evidence we have for physics beyond the standard model. Neutrinos are everywhere. They are produced in the sun, in other stars, in supernova explosions, and in the Earth's atmosphere when cosmic rays strike it. There is even a cosmic neutrino background, similar to the cosmic microwave background left over from the Big Bang. These ancient neutrinos fill all of space. Because they interact so rarely, they can travel across the entire universe without being stopped or deflected. This makes them unique messengers. They can carry information from the hearts of stars or from the most violent cosmic events, places that we can't see with light. Huge neutrino detectors, like the Ice Cube Observatory at the South Pole, are designed to catch the high-energy neutrinos from these distant sources. Ice Cube uses a cubic kilometer of Antarctic ice as its detector, looking for the tiny flashes of light produced when a neutrino happens to interact with an ice molecule. These ghostly particles are a constant, invisible presence in what we call empty space. They are a reminder that the vacuum is not a barrier, but a medium that is constantly being traversed by particles that are almost, but not quite, nothing. Number 13, space itself might have a shape. The universe might be finite, but have no edge. If you traveled in a straight line for long enough, you could end up right back where you started. The overall geometry of space on the largest scales is still an open question in cosmology. It could be flat, like a sheet of paper, or it could be curved. According to Einstein's theory of general relativity, the geometry of spacetime is determined by the total amount of mass and energy within it. There is a critical density. If the actual density of the universe is greater than the critical density, the universe has positive curvature like the surface of a sphere. In this closed universe, space is finite but has no boundary. Parallel lines would eventually converge. If the density is less than the critical density, the universe has negative curvature like the surface of a saddle. In this open universe, space is infinite and parallel lines would diverge. If the density is exactly equal to the critical density, the universe is flat. In a flat universe, space is infinite, and parallel lines stay parallel forever. Our best measurements, primarily from the patterns in the cosmic microwave background, suggest that the universe is very, very close to being flat. The measurements from the Planck satellite show that the curvature of the universe is zero, with a margin of error of only about 0.4%. But flat doesn't necessarily mean simple. Even a flat universe could have a strange topology. Think of a flat sheet of paper. You can roll it into a cylinder, it's still flat on its surface, a triangle's angles still add up to 180 degrees, but it's finite in one direction. You can then connect the ends of the cylinder to make a torus or a donut shape. This is a flat, finite universe with no edge. If you lived in such a universe, you could look in one direction with a powerful telescope and see the back of your own head. Scientists have searched for evidence of such a repeating universe. They've looked for patterns in the CMB that would be created if the light from the early universe had wrapped around and intersected itself. So far, no such evidence has been found. The data suggests that if the universe is finite and wraps around, it must be larger than the part of the universe we can see, our observable universe. The question of the universe's shape is fundamental. It tells us about the ultimate fate of the cosmos. A closed universe with positive curvature would eventually stop expanding and collapse back on itself in a big crunch. Open and flat universes, assuming dark energy continues to dominate, would expand forever, becoming colder and emptier until they suffer a heat death. The fact that the universe is so close to flat is itself a puzzle known as the flatness problem. In general relativity, any deviation from perfect flatness in the early universe should have been magnified enormously over time. For the universe to be so close to flat today, it must have been unbelievably flat at the beginning. The theory of cosmic inflation provides a possible solution. The incredible stretching of space during inflation would have flattened out any initial curvature, just like inflating a balloon makes a small patch on its surface appear flatter. But the ultimate shape and size of space remains one of the great unanswered questions. Number 12, space is not smooth, it's a foaming sea of possibilities. At the smallest possible scales, far smaller than an atom or even a proton, the fabric of spacetime is not smooth and calm. It is a chaotic, turbulent maelstrom of quantum fluctuations. This theoretical concept is known as space-time foam or quantum foam. At these scales, space and time themselves lose their familiar meaning. This idea comes from trying to combine general relativity and quantum mechanics, the two pillars of modern physics. General relativity describes a smooth, continuous space-time. Quantum mechanics describes a world of probabilities and uncertainty. The Heisenberg uncertainty principle says that you can't know certain pairs of properties, like a particle's position and momentum, with perfect accuracy at the same time. There is a fundamental fuzziness to reality. This uncertainty also applies to energy and time. The uncertainty principle allows for tiny amounts of energy to be borrowed from the vacuum for very short periods of time. This borrowed energy can manifest as virtual particles popping into and out of existence. It can also manifest as fluctuations in the geometry of spacetime itself. At the Planck scale, which is an incredibly tiny length of about 10 to the power of 35 meters, these quantum effects on gravity are expected to become dominant. Spacetime itself would be constantly fluctuating. Tiny wormholes and bubbles of spacetime could be constantly forming and disappearing. The smooth geometry of Einstein's theory would break down and be replaced by a roiling probabilistic foam. The physicist John Wheeler, who coined the term spacetime foam in the 1950s, described it this way: if you look at the ocean from a high-flying airplane, it looks smooth. But as you get closer, you see waves. And if you get even closer, you see the foam and bubbles on the surface of the waves. He suggested that spacetime is similar. On the large scales we experience, it looks smooth. But if we could zoom in to the Planck scale, we would see its true chaotic nature. We don't have a complete theory of quantum gravity yet, so the exact nature of space-time foam is still a matter of speculation. Theories like string theory and loop quantum gravity offer different pictures of what space-time is like at these smallest scales. But they all agree that the classical picture of a smooth, passive background is wrong. Are there any ways to test this idea? It's incredibly difficult because the scales involved are so small. But some scientists have proposed that spacetime foam could have subtle observable effects. For example, the constant fluctuations could affect the propagation of light from distant sources. Light of different energies might travel at slightly different speeds through the foam. Astronomers are looking for this effect in the light from distant gamma-ray bursts. A tiny delay in the arrival time of high-energy photons compared to low-energy photons could be a signature of space-time foam. So far, the results have been inconclusive, but the search continues. The idea of quantum foam completely changes our perception of empty space. It suggests that at its most fundamental level, the vacuum is a place of infinite complexity and activity, where the very concepts of distance and duration are constantly being created and destroyed. Number 11, there might be tunnels hidden in spacetime. The empty space might not be simply connected. There could be shortcuts or wormholes connecting distant regions of the universe, or even connecting our universe to another one entirely. These hypothetical tunnels through the fabric of spacetime are allowed by the equations of Einstein's general relativity. The concept is often called an Einstein-Rosen bridge. In 1935, Albert Einstein and his colleague Nathan Rosen were exploring the mathematical solutions of general relativity. They found a solution that described a connection between two different points in spacetime. This was the first theoretical description of a wormhole. A simple analogy is to think of spacetime as a two-dimensional sheet of paper. The distance between 2 points on the paper is a straight line. But if you bend the paper over and poke a hole through both layers, you can create a much shorter path between the 2 points. A wormhole would be a three-dimensional version of this tunnel. The wormholes described by the original Einstein-Rosen solution have a problem, though. They are not traversable. They pinch off so quickly that nothing, not even light, would have time to pass through them. For a wormhole to be useful for travel, it would need to be held open. In the 1980s, physicists like Kip Thorne showed that it might be theoretically possible to have a traversable wormhole. But it would require a special ingredient, exotic matter. This is a hypothetical type of matter that has negative energy density. It would have a kind of anti-gravitational effect, pushing the walls of the wormhole apart and preventing it from collapsing. We have never observed any matter with this property, and it's not clear if it can exist. The Casimir effect shows that regions of negative energy density can exist, but it's uncertain if you could collect enough of it to stabilize a macroscopic wormhole. Even if a stable wormhole could be created, it would come with its own set of problems. Traveling through a wormhole could potentially allow for time travel. If you could connect 2 points in space, you could also connect 2 points in time. This opens the door to all sorts of paradoxes, like the grandfather paradox, where a time traveler goes back in time and prevents their own grandfather from meeting their grandmother, thus preventing their own birth. Some physicists, like Stephen Hawking, have proposed a chronology protection conjecture, which suggests that the laws of physics somehow conspire to prevent time travel on macroscopic scales, perhaps by destroying any wormhole that could be used as a time machine. For now, wormholes remain firmly in the realm of science fiction. There is no evidence that they exist in nature, but they are a fascinating possibility that emerges from our best theory of gravity. They show that the structure of empty space could be far more complex and strange than we can imagine, with hidden connections and shortcuts woven into its fabric. Number 10. Space is filled with a field that gives everything mass. Every particle in the universe gets its mass by interacting with an invisible field that permeates all of space. This is the Higgs field. Without it, fundamental particles like electrons and quarks would be massless and would fly around at the speed of light. Atoms could not form. There would be no stars, no planets, and no people. The idea of the Higgs field was proposed in 1964 by several physicists, including Peter Higgs. They were trying to solve a problem in the standard model of particle physics. The theory that describes the electromagnetic and weak nuclear forces worked beautifully, but it only worked if the force carrying particles were massless. We knew from experiments that the particles that carry the weak force, the W and Z bosons, are in fact very massive. The proposed solution was the Higgs mechanism. The idea is that the entire universe is filled with a field, the Higgs field. As particles move through this field, they interact with it. This interaction, this drag, is what we perceive as mass. Some particles, like the photon, don't interact with the Higgs field at all, so they have no mass and travel at the speed of light. Other particles, like the top quark, interact very strongly with the field, so they are very massive. A common analogy is to think of the Higgs field as a room full of people at a party. A famous person walks into the room. People cluster around them, making it difficult for them to move. They have acquired a lot of mass. An unknown person can walk through the room much more easily, with very few people stopping to talk to them. They have very little mass. Just like other quantum fields, the Higgs field should have a particle associated with it. This particle is the Higgs boson. It's an excitation of the field, like a wave on the surface of a pond. Finding the Higgs boson was the primary goal of the Large Hadron Collider, LHC, at CERN. The LHC is a 27-kilometer ring of superconducting magnets that smashes protons together at nearly the speed of light. In these high-energy collisions, new particles can be created. On July 4th, 2012, scientists at the LHC announced that they had discovered a new particle with the properties predicted for the Higgs boson. It was a historic moment that confirmed the existence of the Higgs field. The Higgs field is a fundamental component of the vacuum. Unlike other fields, like the electromagnetic fields, the Higgs field has a non-zero value everywhere, even in what we consider to be empty space. This is its ground state. The fact that the vacuum is filled with this field is what breaks a fundamental symmetry of the laws of nature and gives particles their mass. So when you look at an empty part of the room, it's not empty. It's filled with this invisible substance, this cosmic molasses, that is responsible for one of the most basic properties of matter. The Higgs field is a constant, universal presence that makes the universe as we know it possible. Number 9, space is laced with giant, invisible magnetic fields. Vast regions of empty space between galaxies are not truly empty. They are threaded by weak but enormous magnetic fields. The origin of these intergalactic magnetic fields is one of the great unsolved mysteries in astrophysics. They seem to be everywhere, even in the most remote voids of the cosmos. We are familiar with magnetic fields on Earth generated by the molten iron core of our planet. The sun has a powerful magnetic field, which drives sunspots and solar flares. Our Milky Way galaxy has its own magnetic field, which is about 1 million times weaker than Earth's, but extends over tens of thousands of light years. These galactic fields are thought to be generated by a dynamo effect, where the motion of charged particles in the rotating galaxy amplifies small seed fields. But in the 1990s, astronomers began to find evidence for magnetic fields in places where there are no galaxies, in the vast voids between galaxy clusters. They used radio telescopes to study the light from distant quasars. As this light travels through an intergalactic magnetic field, it interacts with the charged particles in the tenuous intergalactic gas. This interaction, called Faraday rotation, twists the polarization of the radio waves. By measuring this twisting, astronomers can infer the strength and direction of the magnetic field along the line of sight. These studies have shown that magnetic fields seem to be a universal feature of the cosmos. They are weak, typically a billion times weaker than the Earth's magnetic field. But they are coherent over immense scales, millions of light years across. The puzzle is, where did they come from? The dynamo mechanisms that work in galaxies don't seem to work in the voids, where there is very little matter and motion. One possibility is that these are primordial magnetic fields, created in the very early universe, perhaps during the period of cosmic inflation or during a phase transition shortly after the Big Bang. If this is the case, these fields would be a fossil from the first moments of creation, providing a unique window into the physics of the early universe. Another possibility is that these fields were ejected from galaxies. Supernova explosions and jets from supermassive black holes can drive powerful outflows of gas and magnetic fields out of galaxies and into intergalactic space. Over billions of years, these outflows could have seeded the voids with magnetic fields. Distinguishing between these scenarios is difficult. Astronomers are using new radio telescopes like the Square Kilometre Array Sky to map these cosmic magnetic fields with unprecedented detail. By studying how the strength and structure of the fields change with cosmic time, they hope to piece together the story of their origin. These giant invisible fields are another layer of complexity in what we call empty space. They can influence the formation of galaxies, guide the paths of high-energy cosmic rays, and carry energy and momentum across vast cosmic distances. The vacuum is not just a passive void, it's a magnetized medium that plays an active role in the evolution of the universe. Number 8. Empty space can spontaneously create matter. Under the right conditions, empty space can erupt with matter. If you create an electric field that is strong enough, the virtual electron-positron pairs that are constantly flickering in and out of existence in the quantum vacuum can be torn apart and become real, stable particles. This process is called the Schwinger effect. The idea goes back to Paul Dirac's work on antimatter. The vacuum is not empty, but a sea of virtual particle-antiparticle pairs. These pairs pop into existence for a fleeting moment, borrowing energy from the vacuum, and then annihilate each other, paying the energy back, all in compliance with the Heisenberg uncertainty principle. Normally, we don't notice this quantum foam, but what happens if you apply a very strong electric field to this vacuum? An electric field pulls positive charges in one direction and negative charges in the other. A virtual electron-positron pair consists of a negative electron and a positive positron. The electric field will pull them in opposite directions. If the field is strong enough, it can pull them far enough apart that they can't find each other to annihilate. If they gain enough energy from the field to equal their rest mass energy E equal mc squared, they can become real particles. The vacuum itself sparks, creating matter and antimatter from nothing but the energy of the field. The problem is that the required electric field is immense. It's called the Schwinger limit, and it's about 100 million trillion volts per meter. This is a field strength far beyond what we can create in a laboratory with conventional methods. To put it in perspective, the field required to cause a spark in the air lightning is about 3 million volts per meter. The Schwinger limit is vastly larger. However, there are places in the universe where such extreme fields might exist. Such places around magnetars. These are a type of neutron star with incredibly powerful magnetic fields, the strongest in the universe. The changing magnetic fields around a magnetar can induce electric fields that might be strong enough to approach the Schwinger limit. Astronomers believe that the production of electron-positron pairs from the vacuum plays a key role in the powerful bursts of radiation we see from these objects. Scientists are also trying to find ways to observe this effect in the lab. One promising approach is to use extremely powerful lasers. By focusing two intense laser beams, it might be possible to create a combined electromagnetic field that is strong enough to rip particles out of the vacuum. And experiments at facilities like the Extreme Light Infrastructure ELI are being designed to push laser technology to these limits. The Schwinger effect is a powerful demonstration of the physical reality of the vacuum. It shows that empty space is not just a stage for matter and energy, but is itself a substance that can be polarized, stressed, and ultimately broken down to create something from nothing. Number 7, spooky connections can exist across any distance. Two particles can be linked in such a way that measuring a property of one particle instantly influences the property of the other, no matter how far apart they are. This phenomenon, called quantum entanglement, can happen across a room or across a galaxy. Albert Einstein famously called it spooky action at a distance. It is one of the most bizarre and counterintuitive features of quantum mechanics. Imagine you have two entangled particles, say two photons. They are created in such a way that their properties are correlated. For example, their polarizations might be linked. If you measure the polarization of one photon and find it to be vertical, you will instantly know that the other photon, if measured in the same way, will have a horizontal polarization. The strange part is that before the measurement, neither photon has a definite polarization. They exist in a superposition of all possible states. It is the act of measuring one that forces both of them to choose a state. This instant connection seems to violate the cosmic speed limit, the speed of light. If the two particles are light years apart, how does the second particle know what measurement was made on the first one instantly? And Einstein thought this meant quantum mechanics must be incomplete. He believed there must be some hidden variables, some pre-existing properties of the particles that we just don't know about, which determine the outcome of the measurement in advance. However, in the 1960s, a physicist named John Bell devised a mathematical theorem, now known as Bell's theorem. It showed that you could perform experiments to distinguish between the predictions of quantum mechanics and the predictions of any theory based on local hidden variables. In the decades since, numerous experiments have been performed, and they have all confirmed the predictions of quantum mechanics. There are no hidden variables, the spookiness is real. It's important to understand that entanglement does not allow for faster-than-light communication. While the influence is instant, you cannot use it to send a message. To know that the state of the second particle has been determined, you still need to communicate the result of the first measurement to the person with the second particle, and that communication is limited by the speed of light. Entanglement is not just a theoretical curiosity, it is a real physical phenomenon that is being harnessed for new technologies. Quantum computing uses entanglement to perform calculations that are impossible for classical computers. Quantum cryptography uses entanglement to create perfectly secure communication channels. This spooky connection exists in the vacuum of space. Two entangled particles can travel for billions of years across the cosmos, and their mysterious link will remain intact. This tells us that empty space is not a simple separator. It is a stage that allows for these profound, non-local connections, weaving a web of interconnectedness that defies our classical intuition about distance and separation. Number 6, space is not actually empty at all. Even in the deepest intergalactic void, far from any stars or galaxies, a cubic meter of space is not empty. It still contains, on average, a few hundred photons of the cosmic microwave background, a handful of neutrinos, and about one hydrogen atom. What we call empty space is just a matter of degree. The density of matter in the universe varies enormously. In the core of a neutron star, matter is so dense that a teaspoonful would weigh billions of tons. In the Earth's atmosphere at sea level, there are about 25 million trillion molecules in every cubic centimeter. But as you go up, the density drops rapidly. In the vacuum of low Earth orbit, where the International Space Station flies, there are still trillions of particles per cubic centimeter. This is a better vacuum than we can create in most labs on Earth, but it's still far from empty. It's enough to cause a noticeable drag on satellites over time. As you move farther out into the space between the planets, the density drops further. The solar wind, a stream of charged particles from the sun, fills this region. The density is only about 5 to 10 particles per cubic centimeter. Then you leave the solar system and enter interstellar space, the space between the stars in our galaxy. This is the interstellar medium. It's not a perfect vacuum either. It's filled with a tenuous mix of gas, mostly hydrogen and helium and tiny grains of dust. The average density is about 1 atom per cubic centimeter, but it's very clumpy. There are dense molecular clouds where the density can reach millions of atoms per cubic centimeter, which are the birthplaces of new stars. There are also vast, hotter, more diffuse regions. Finally, you travel out of our galaxy and into intergalactic space, the vast voids between the galaxies. This is the emptiest place we know of. But even here, it's not a perfect nothing. There is the warm, hot intergalactic medium WIM, a web of superheated gas that is thought to contain a significant fraction of all the normal matter in the universe. The average density is incredibly low, maybe 1 atom per cubic meter. So on a purely practical level, no region of space is truly perfectly empty of matter. But even if you could somehow remove every last atom, every last photon, and every last neutrino, the space would still not be empty. As we've seen, it would still be filled with the Higgs field, dark energy, dark matter, and the seething energy of the quantum vacuum. The idea of a perfect void is a philosophical concept, not a physical reality. The cosmos is a messy, busy place. The emptiness of space is really just the lowest density state of a very complex and active substance. Number 5, empty space exerts a physical force. 2 uncharged, perfectly smooth metal plates placed fractions of a millimeter apart in a perfect vacuum will be pushed together by the vacuum itself. This strange phenomenon is called the Casimir effect. It is direct, measurable proof that the empty space between the plates is not empty, but is teeming with quantum energy. The effect was predicted in 1948 by the Dutch physicist Hendrik Casimir. He was working at Phillips Research Labs studying the forces between molecules. His calculations led him to consider the effects of the quantum vacuum. According to quantum field theory, the vacuum is filled with virtual electromagnetic waves, or photons of all possible wavelengths, constantly popping in and out of existence. Casimir realized that if you placed 2 parallel plates close together, they would act as a resonant cavity. Only virtual photons, whose wavelengths fit a whole number of times between the plates, can exist in the space between them. Longer wavelengths are excluded. However, outside the plates, there is no such restriction. Virtual photons of all wavelengths can exist. This means there are more virtual photons pushing on the plates from the outside than there are from the inside. This imbalance in the radiation pressure of the quantum vacuum creates a net force that pushes the plates together. The closer the plates are, the fewer wavelengths can fit between them, and the stronger the force becomes. For decades, this was just a theoretical prediction. The force is incredibly weak and difficult to measure. It only becomes significant at very small distances, on the order of microns. But in 1997, Stephen Lamoureux at the University of Washington managed to measure the Casimir force for the first time, using a sensitive torsion pendulum. His results matched the theoretical predictions with an accuracy of about 5%. Since then, many other experiments have confirmed the existence of the Casimir effect with even greater precision. The Casimir effect has real-world implications, especially in the field of micro and nanotechnology. As engineers build smaller and smaller mechanical devices, the Casimir force can become a significant problem, causing tiny parts to stick together. But its most profound implication is what it tells us about the nature of the vacuum. The Casimir effect is not caused by any matter or known force field. It is a force from nothing. It is a direct manifestation of the zero-point energy of the vacuum, the energy that remains even at absolute zero temperature. It shows that the quantum fluctuations in empty space are not just a mathematical abstraction. They are real, and they have real physical consequences. The vacuum is not passive. It can push and pull on the world of matter. Number 4, space and time are a single, interwoven fabric. The 3 dimensions of space and the 1 dimension of time are not separate entities. They are inextricably linked together into a single 4-dimensional continuum called spacetime. The way you experience space depends on how you are moving through time, and vice versa. An event does not happen at a place, it happens at a place and a time. This revolutionary idea was first proposed by Hermann Minkowski in 1908 as a way to better understand his former student Albert Einstein's theory of special relativity. Einstein's theory had shown that measurements of distance and time are relative. 2 observers moving at different speeds will disagree on the length of an object and the duration of a time interval. Minkowski showed that while space and time are relative, space-time is absolute. All observers, no matter how they are moving, will agree on the distance between 2 events in 4-dimensional spacetime. This unified spacetime is the stage on which the universe plays out. But it's not a static stage. In 1915, Einstein extended his theory into general relativity, which is our modern theory of gravity. General relativity reveals that spacetime is not just a passive background. It is a dynamic physical object that can be bent, warped, stretched, and twisted by the presence of mass and energy. What we feel as the force of gravity is not a force at all. It is simply the curvature of space-time. The Earth is not being pulled towards the sun by a mysterious force. Instead, the massive sun warps the space-time around it. The Earth is simply following the straightest possible path, a geodesic, through this curved spacetime. It's like a marble rolling on a stretched rubber sheet with a bowling ball in the middle. The marble is not attracted to the bowling ball, it's just following the curve in the sheet created by the ball's weight. This warping of spacetime affects both space and time. Near a massive object where gravity is strong, time literally runs slower. This is not a trick of perception, it's a real physical effect. The GPS satellites in orbit around the Earth have to account for this. Their clocks run slightly faster than clocks on the ground because they are in a region of weaker gravity. If their software didn't correct for this effect of general relativity, the GPS system would accumulate errors of several kilometers every day. The idea that space is not a fixed, absolute grid, but a dynamic substance that can be shaped by matter is one of the most profound shifts in thinking in the history of science. It means that the geometry of the universe is not a given. It is determined by the contents of the universe. The stage and the actors influence each other. Empty space is not an empty container, it is the gravitational field itself. Number 3, extra dimensions of space might be all around us. Our universe might have more than the 3 spatial dimensions we experience. There could be extra hidden dimensions of space curled up to a size so small that we have never noticed them. The fundamental particles and forces we see might just be vibrations and movements in these extra dimensions. The idea of extra dimensions is not new. It was first proposed in the 1920s by Theodore Kaluza and Oskar Klein. They were trying to unify the 2 known forces of their time, gravity and electromagnetism. Kaluza discovered that if he wrote down the equations for Einstein's theory of gravity in a universe with 5 dimensions, 4 of space, 1 of time, the equations naturally split into 2 sets. One set was the original equations for gravity in 4 dimensions. The other set was Maxwell's equations for electromagnetism. This suggested that electromagnetism could be understood as gravity acting in a hidden 5th dimension. To explain why we don't see this 5th dimension, Klein proposed that it is compactified. It's curled up into a tiny circle. An analogy is a garden hose. From far away, it looks like a one-dimensional line. But if you look closely, you can see that at every point on the line there is a second dimension, a little circle you can move around. Klein suggested that the extra spatial dimension is curled up into a circle with a radius so small, on the order of the Planck length, that it is completely undetectable to us. For many years, this Kaluza-Klein theory was seen as a mathematical curiosity, but the idea of extra dimensions was revived in the 1980s with the development of string theory. String theory proposes that the fundamental constituents of the universe are not point-like particles, but tiny, vibrating, one-dimensional strings. The different ways a string can vibrate correspond to the different particles we see, like electrons and photons. One of the strange requirements of string theory is that it only works mathematically in a universe with more than 4 dimensions. The most popular versions of the theory require a total of 10 or 11 spacetime dimensions. Just like in the Kaluza-Klein theory, these, extra dimensions are thought to be compactified, curled up into complex shapes known as Calabi-Yau manifolds. The specific geometry of these hidden dimensions determines the properties of the strings, and thus the laws of physics that we observe in our 4-dimensional world. Some more recent theories known as brain world scenarios have proposed that the extra dimensions might not be so small after all. In these models, our 4-dimensional universe is a brane short for membrane floating in a higher dimensional space called the bulk. The particles and forces of the standard model are confined to our brain, which is why we can't see into the extra dimensions. But gravity, which is the curvature of space-time itself, could be able to leak into the bulk. This could explain why gravity is so much weaker than the other fundamental forces. Scientists are searching for evidence of extra dimensions at particle accelerators like the LHC. If two particles collide with enough energy, they might be able to create a new particle that travels off into an extra dimension. This would appear in our detectors as a loss of energy and momentum. So far, no such evidence has been found. But the possibility that the empty space around us is hiding a rich, complex geometry of unseen dimensions remains one of the most exciting and mind-bending ideas in modern physics. Number 2, the universe may have been born from a fluctuation in nothing. Our entire universe, with its hundreds of billions of galaxies, might have originated as a random quantum fluctuation in a pre-existing state of nothingness. In this view, the Big Bang was not the beginning of everything, but simply the moment when a bubble of space-time like ours burst into existence from a timeless, spaceless quantum foam. This idea that the universe could be the ultimate free lunch comes from trying to apply quantum mechanics to the cosmos as a whole. The law of conservation of energy says that energy cannot be created or destroyed. So how could an entire universe full of energy appear from nothing? The answer might be that the total energy of the universe is actually 0. The universe is full of positive energy in the form of matter and radiation, but it is also full of negative energy in the form of gravity. Every object with mass exerts a gravitational pull on every other object. To pull these objects apart, you have to do work, which means you have to add energy to the system. This means that the gravitational field has negative energy. It is possible that the total positive energy of all the matter and radiation in the universe is perfectly balanced by the total negative energy of gravity. If the total energy is 0, then there is no violation of the conservation of energy in creating a universe from nothing. Or quantum mechanics tells us that nothing, the vacuum, is not truly empty. It is subject to quantum fluctuation. The uncertainty principle allows for energy to be borrowed from the vacuum for short periods. Normally, this results in virtual particles, but if you have a theory of quantum gravity, it's possible that a fluctuation could create not just a pair of particles, but a tiny nascent universe. The theory of inflation provides a mechanism for how such a tiny universe could grow into the vast cosmos we see today. A small patch of space-time, perhaps just a fraction of a millimeter across, could be created by a quantum fluctuation. If this patch contained a field with the right properties, an inflaton field, it would immediately begin to expand at an exponential rate. Within a tiny fraction of a second, it would have stretched to an enormous size. The energy from the inflatoned field would then be converted into the matter and radiation of the hot Big Bang, and the universe would continue its more leisurely expansion. In this scenario, our Big Bang was not a unique event. Quantum fluctuations could be constantly creating new universes in a larger multiverse. This provides a possible explanation for why our universe exists at all. If the creation of universes from nothing is a possible physical process, then given enough time or in a timeless state, it is not just possible but inevitable that universes like ours would come into being. This is a highly speculative idea on the very edge of our scientific understanding. We don't have a complete theory of quantum gravity, so we can't be sure if this picture is correct. But it is a powerful idea that arises from combining our two most successful theories of the universe. It suggests that the ultimate origin of all the complexity and structure we see around us could be a random event in the simplest possible starting point, a state of absolute nothingness. Number 1, the vacuum is a raging sea of phantom particles. A perfect vacuum, completely empty of all matter and radiation, at a temperature of absolute zero, is still a place of furious, ceaseless activity. It is a seething cauldron of virtual particles, pairs of matter and antimatter that pop into existence from nothing and then annihilate each other in an unimaginably short time. This is the zero-point energy of the vacuum, the baseline level of activity that can never be removed. This is a direct consequence of the Heisenberg uncertainty principle, a cornerstone of quantum mechanics. The uncertainty principle states that there is a fundamental limit to how precisely you can know certain pairs of physical properties. One such pair is energy and time. You can't know the exact energy of a system over an infinitely short period of time. This allows for tiny amounts of energy to be borrowed from the vacuum, as long as the loan is paid back very quickly. The amount of time the energy can be borrowed for is inversely proportional to the amount of energy borrowed. A small amount of energy can be borrowed for a longer time, while a large amount of energy can only be borrowed for an extremely short time. This borrowed energy can manifest as particles. According to E=mc², energy and mass are equivalent. So a borrowed fluctuation of energy can take the form of a particle-antiparticle pair, for example, an electron and a positron. These are not real particles in the sense that we can see them with a detector. They are virtual because they exist for such a short time on borrowed energy that they cannot be directly observed. They exist on the very edge of reality, but their effects are very real. We have already seen some of these effects. The Casimir effect, the force that pushes two plates together in a vacuum, is caused by the pressure of these virtual particles. The Schwinger effect is the idea that a strong enough electric field can turn these virtual pairs into real ones. Virtual particles also play a crucial role in our understanding of fundamental forces. In quantum field theory, forces are described as being carried by the exchange of virtual particles. For example, the electromagnetic force between two electrons is described as the exchange of virtual photons. The Lamb shift is another key piece of evidence. It's a tiny difference in the energy levels of the hydrogen atom that was first measured in 1947. According to Dirac's original theory, these energy levels should have been identical. The explanation for the shift is the interaction of the electron in the hydrogen atom with the virtual particles of the vacuum. The electron is constantly being jostled by the sea of virtual photons, which slightly changes its energy. The theoretical calculations of the Lamb shift, which include these vacuum effects, match the experimental measurements with incredible precision. The vacuum is the ground state of the universe, the state of lowest possible energy. But in quantum mechanics, the ground state is not a state of rest, it is a state of minimum activity. The quantum vacuum is the ultimate source of this activity. It is the physical embodiment of the uncertainty and potentiality that lies at the heart of quantum reality. Far from being a peaceful void, the empty space that surrounds us is the busiest, most dynamic, and perhaps the strangest place in the entire cosmos.